Okay, it says at high temperature, sulfur dioxide and nitrogen dioxide react according to the equation below. Determine the equilibrium constant for the reaction. To do this, construct an ice table, part 1, then the equilibrium expression, and solve it, part 2. Complete parts 1 and 2 before you submit your answer. Okay, it says a 1.00 liter reaction vessel was filled with 2.0 moles of sulfur dioxide and 2.00 moles of nitrogen dioxide. At equilibrium, there was 1.30 moles of NO in the vessel. Fill in the ice table with the appropriate values for each value of each involved species. Okay. Okay, so 2. Okay. I see what you mean, but it's not letting you. Oh, okay. Oh, good. I was like, it's not letting me put things in there. Okay. Ammonium, nitrogen dioxide, 2. Okay. The change. Oh, okay. But if we think about it, at equilibrium, don't we have a value at equilibrium? It says at equilibrium, there was 1.30 moles of. So if this is 1.30 moles of NO, that's our equilibrium value. That's also going to be our change value, right? So then if there's 1.30 moles of NO, then how many moles of, I can't even read that. Is that SO3? Okay. Isn't it a 1-to-1 ratio? So what should the value be? Should it be? So then these values should be negative. So then this value should be, right? Yeah, and well, it's because it's a multiple ratio. It was all 1, right? And then also the fact that we can do that because we also have 1 liter, right? Okay. So then if we're going to calculate our K value, can I hit plus? Oh, no, you go to the, or I go to, oh. See, that shows you how much. So now I get to solve for my K value, right? So then I have, got to go back to the original table because I can't remember the numbers. What was it? The top was 1.3, right? Yeah. And then okay. And then Okay. They should do the math for me since I'm lazy. What did you guys get? $3.4. Okay. And then I hit plus. Or she'll answer. Hey, correct. It's the same thing, and even with the regular ice table. The only thing. No, you're not assuming, they're telling you, right? So there's no assumptions that are being made here. They're saying this that at equilibrium, there is 1.30 moles of NO, right? Since it's a 1-to-1 ratio, at the very beginning, you're starting off with no NO, right? And you end up with 1.3 moles of NO. So then that means that by default, since this is a 1-to-1 ratio, that's going to be exactly the same amount that you have here, right? Does that make sense? Yeah, it's because they gave you everything. You're like, what? No, that can't be right. And your first instinct is like, no, that can't be right. They're not giving me everything. I should be trying to solve for X, right? Yeah. Instead, they gave you X. Yeah. Any other questions? You have a captive audience, so take advantage of it. So, which question? You guys don't wait till the last day to do all your homework, do you? Just asking. I'm looking at these numbers here. I'm like, hmm. Oh, it tells me. It tells me everything. I can tell you when you did it too, right? If I really wanted to look. Yeah. 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 If I had a lot of extra time, I used to be a stalker, like, hey, this person, and then I corner them and, hey, why haven't you done your homework? The one, the special one. Okay. Okay. Oh, I'm gonna find out. I'm gonna be checking it every day. I'm gonna say, okay, Moses. 41. Okay. It says an initial gas sample of NOBr decomposes according to the reaction below. Predict the concentration of NO at equilibrium. Construct an ice table, part 1. Write the equilibrium constant expression, part 2. Then solve for the concentration of NO at equilibrium. Complete 1 through 3 before submitting your answer. Okay. Okay, so let's go ahead and. Okay.
going down for the change is going to be negative. Oh, I mean, across 0,
0, 0. Okay.
It'll be negative, right? And it's going to be 2x plus 2x. Put on the right hand side. X plus x.
Oops. There's plus X. Okay.
And then it's going to be 0.20 minus 2x.
0.20 minus 2x. Oops. Right here. Fourth time's the charm.
And then it's going to and then we go to the second. So I want to see how you solve it. It must be maybe the solve it the reaction. So on top of it going to be 2x squared.
Oops, sorry, 2x squared.
Going to be times x. So 0.20 minus 2x squared. That'll be that one.
Okay. Because the equation, it has 2, and so we have to square it. Right. Yep.
And the thing is, I solved it, but I want to see how you kind of solve it because I similar to the one that we also took on the
Oh,
other
shit.
day.
Sorry about that. Oh, crap. Okay. Well, let me just put the equation back in, and then we'll go through it and solve it. Okay. So we had 2x squared, and then we had x, and then we had all over. Okay. So look at our number. It doesn't work.
Yeah, I rechecked it 2 times, but I kind of want to go to the
Third power.
yeah, and I was like, I don't want to be thinking of decimal.
Yeah. So are you sure? Because that number is, I guess it's not too small, but small enough typically. But the 5% doesn't work. So let's try with the 5% first, and then we'll see. Right? What's that? Yeah. Okay, so let's go ahead and we'll make the assumption. Can you guys see my screen on the other side?
Yeah.
So I'm going to neglect this here, right? So then we'll get 0.2 squared over 4x cubed. And that equals 3.07 times 10 to the minus 4. So we get So we get 4x cubed equals 3 point, sorry. Brain is working on autopilot here. 1.2 times 10 to the minus 5. So if we take the, divide that by 4, so we get x cubed equals 3.07 times 10 to the minus 6. So that x is going to equal you are still right. So x is going to equal 0.0145.
That's what I want.
Okay. And so divide that by 2. Yeah, 2, we get 7% more. So it's a little off, yeah. So, okay. That means we got to do it the hard way, right? So if we do it the hard way, so I'm going to go back to where we started from up here. Actually, hold on 1 second. That's not what I wanted to do. What was that?
Are you looking for the
Yeah, the bottom part, it was
bottom part with
0.20 minus 2x, right? Squared. Okay. Okay, so then we end up with 0.04. Is that right? Correct me if I'm wrong. Minus 2, so minus 0.08. Zero x plus 4 squared. Oops. 3.07 times 10 to the minus 4. Okay, so then we bring this guy over. So we end up with 4x cubed equal to 1.23 times 10 to the minus 5 minus times 7. 2.46 times 10 to the minus 4 x plus 1.23 times 10 to the third x squared. 10 to the minus 3 x squared. I ran out of x squared. Okay, so then I have 4 x cubed minus 1, 2, 3 times 10 to the 23rd. I'm sorry, not 10 to the 10 to the minus 3 x squared plus 2.46 times 10 to the minus 4 x plus, whoops, sorry, minus 1.23 times 10 to the minus 5.
Yes,
Okay.
that's exactly what I was doing, but like, I don't know how to.
How you solve it?
Well, I know how to
Sure.
record by grouping, but kind of.
Okay, so let me show you how I would go about solving it. Okay, you see my beautiful spreadsheet? Okay, so I'm gonna type in the equation so that we have the equation. So we have 4x and then cubed, right? So I'm going to use cubed plus, oops, sorry, minus 1.23 e to the -3 times x squared sorry, it's been a long day, gotta bear with me, it's gonna take a minute, plus 2.46 e to the -4 times x minus 1.23 e to the -5. Okay, so that's our equation. So let me adjust this so that it will behave the way I want it to. Okay. Okay, so I'm going to clear. Do you guys mind if I clear all of the work that we've done? Okay, maybe. Okay, so now I need to define what x is, right? So I'm going to say x, and then say x equals, and I'm going to put a value, where is it? Our value that we're going to start at is 0.20 because that's what our starting point is. 0. Okay, so then I need to make a definition of x. So insert I can hardly see, so I'm going to go to formula and then define name. And it says x. Doesn't it say x? Yes, it says x. Okay. Okay, so what? This is the answer you got? No, it shouldn't be the answer you got yet. Okay, so now we need to sit there and we want to set a goal for this, right? So we want to do, see. Sorry, I cannot see anything these days. Old age. Got to go to data, right? And then you see what if analysis, goal seek. And so we're going to set this guy to 0 by changing this cell. Okay. So let's see. I think it already did it. Okay. So the value that it got is 0.058889, and that's going to get us 0.0008. What answer did you get? Mm-hmm.
was 0.13.
You got 0 point.
And excuse me, my final, that's the final.
This is the final answer for
Yeah,
X.
my final answer was 0.0.
See, he said 0.026. Let's plug it in. 0.206. So that's 10 to the minus 8. Here, let's do this then. Hold on. So, what was it? 60. So that's 1, 2, 3. So then let's do this. We'll multiply this guy by 10 to the, let's go, 10 to the 6. Make sure I enter this right. Okay. That will seek. What if we'll seek? We're setting that value to 0 by changing this value. So by changing this value, it's 0.013229. So what was the answer that you put in?
My final answer for the there was a third step.
Uh-huh.
So that was 0.0.
Okay, hold on. It's actually not cheap. Zero point zero two six.
No, my question wasn't like, my question was this type of question beyond the test because they say like.
No, this type of question won't be on the test. Yeah. Yep. No, this question will not be on the test. That's interesting. And then even with the 0.26, that isn't actually. Yeah. Yeah. So no, I would not put a question like this on the test. Yeah. I'll have to pay closer attention so that I don't. Yeah. I said I have to pay close attention that I don't, because I don't want you shouldn't have to go through that much hassle to get it. You should be able to do it with a quadratic formula or something like that. Yeah. Okay. Questions? Any other questions? Okay. Okay, so let's go ahead and start back up with the lecture. So the relative strengths of acids. You don't think so? Okay, so basically a strong acid is always going to be defined as one that completely ionizes. So basically means that it separates. Weak acids are going to be ones that don't completely separate, right? So for example, if we take the definition of the Bronsted-Lowry acids as proton donors. So a strong acid is going to separate into its ionic components. Strong acid is going to basically yield 100% of the hydronium ion. Weak acid yields much less than 100% of the hydronium ion. These guys, these are 6 strong acids. These are 6 strong bases. So we've talked about acid ionization, and the acid ionization constant is called Ka, right? Or the equilibrium constant for an acid. So your Ka values are going to also tell us the strength of those acids, right? So if you have a large Ka value, then you're going to have a strong acid. And if you have a small Ka value, you're going to have a weak acid. Okay. Yeah. So, and that makes sense, right? Because if it's a large value for your Ka, that means that you have more of this ion, right? Compared to it still being together. If it's a small value, that means that this value is going to be greater than this guy, right? Yeah, yeah. But it makes sense now? Okay. Okay, so in terms of the relative strengths of bases, so we know that bases are going to be proton acceptors, H plus acceptors. So a strong base is going to be that base that completely ionized, nearly 100%, right? So you get the formation of just that hydroxide ion. A weak base is going to yield a much less than 100% hydroxide. So the constant for bases is called Kb, or the auto ionization of bases. So if we put the base into water, we get our conjugate acid and we get hydroxide. So this is going to work exactly the same way. So if I have a large value for Kb, that means that it's going to be more basic compared to if I have a small value for Kb. Okay, Kb and Ka are going to be inversely related. So what does that mean? So Ka of Hb and Kb of B minus is going to equal Kw. So the larger Ka of the acid, the smaller the Kb of the conjugate base. The larger the Kb of the base, the smaller the Ka of the acid. Okay, so if we have Ha plus water yields the hydronium ion and water, hydronium ion and the conjugate base. So the extent of which an acid is donates a proton to water is going to be dependent on the strength of its conjugate base. Right. So in other words, if you have a very strong conjugate base, it's going to actually be driving the reaction the other way. Right. Does that make sense? So if A minus is a strong base, then any protons donated in water molecules are going to be recaptured by the Ka. Right? So in other words, you're going to have little to none hydronium ion, but you're going to have more HA present. So then that means if you're going to have more HA present, that means it's going to be a weak acid. Okay. So if the conjugate base is a weak base, then it is unlikely to recapture the proton. So then that basically means that we have low concentrations of this guy. So that means that the acid is going to be driving in this direction. So therefore, the HA is going to be a strong acid. Here are some examples. This is on the acidic scale. So the hydronium ion is 1 Ka. This is the chlorous acid. This is hydrogen fluoride. This is carbonic acid. This is acetic acid. This is the ammonium ion. This is hydrogen phosphate ion. And then, of course, this is water. So the hydronium ion, strong acid. We know that chlorous acid is going to be a weak acid because it has the OUS. We know that hydrofluoric acid is a weak acid. And we also know that carbonic acid is a weak acid because that's carbon. Same thing with acetate. Okay, so all of these guys are examples of weak acids. Now here, these are examples of weak bases. So this is the chlorite ion. This is the fluoride ion. This is the bicarbonate ion. This is the acetate ion, ammonia. This is the phosphate ion, and then this is OH. So you can see OH is a strong base. Phosphate is a relatively strong base, but everything else are weak. Okay. Questions? Okay. Good. And if we look at the scales, you see how they're opposite. Strong acid this way, weak acid here. Weak base here, strong base here. So the conjugates of each other. This guy's a strong base. This is a weak acid. Okay, questions? Cash, Kool-Aid. And you said you want a copy of this. I'm going to see if I can get a better image of it for you. This one? Okay. Yeah, I'll try to get it for you. I think we did go over this. Or maybe this might be the second time I showed it. Second time. Okay. Okay, so you guys already seen this. Okay, so let's start talking about acid-base reactions. So this equation here, our Kw times our Kb is going to equal, Ka times Kb is going to equal Kw. Okay, so, and that's, keep in mind, this is dealing with conjugate base pairs, right? So for instance, O2. So acetic acid plus H2O equilibrium with its conjugate base. Conjugate base is going to be acetate. 2 H3 O2 minus plus H3 O plus. So this is the acid. This is its conjugate base. Sorry, right? Acid base, yeah, conjugate base, conjugate acid. Okay. So questions? No questions? So if we look at this equation here, so this is for the acid right here. So if we did it for the base, C2H3O2 minus plus H2O. So what is going to be the conjugate base and conjugate acid on the other side? Was that? Sort of flip it. So we'll end up with HC2 H3O2 and nope, OH. Right. Okay, so if we look at each one independently, right, we know that Ka equals, in this case, I'm just going to use the abbreviation HA, okay, for my acid. So Ka is going to equal HA over A minus times H3O plus. Of course, we know this is in brackets. Okay, so Kb is going to be A minus over HA OH. So if I plug it into this equation down here, my Ka, so I get A minus H3O plus over HA times KB, which is HA. H. Brain's working faster than my hands. OH minus over A minus equals KW. Okay. Okay, A minus crosses out with A minus. HA minus, HA crosses out with HA. So then I'm left with just the concentration of the hydronium ion times the concentration of the hydroxide ion equals KW. Which we know is 1.0 times 10 to the minus 14. Can you guys do me a favor? The lab, did you guys get a copy of the lab? Okay. Can you guys get the stuff up first? I didn't have a chance to do it today. Okay. Do you guys see that? Yeah, this semester is heavily math, right? Not hard math, but it's just, yeah. Okay, so let's move forward. Okay, so there are several ways to calculate or to determine the Ka or the Kb of a weak acid or weak base. I'm going to show you a couple of those approaches. Okay, one of the approaches is to measure the pHs of solution and determine by dissociation of the known amounts of weak acid and weak bases. And these, you're typically given, these problems, you're going to be given your pH. You're going to be given some information about the concentrations, and then you should be able to calculate your Ka and Kb. Ka or Kb. Okay, so one of these ways is using the percent ionization. So percent ionization is just going to be the concentration of the hydronium ion at equilibrium divided by the initial concentration of HA. And so that gives us how much ionization has occurred in this situation. Okay. So let's assume that we have, an acid HA equals 0.5 molar HA naught. And then let's assume that we have a pH of 2. What is the percent ionization? So pH of 2 at equilibrium. Did I not give that's right there on the table? Oh wait, those are, yeah, that is right, Keith. Yeah. Okay, first thing I'm going to do is do what? The what? So if I want the percent ionization, will I need to do the ice table? This is at equilibrium. Okay. So would it be 2 over 0.25? No. What is pH? What is the definition of pH? pH equals what? How do I calculate pH? Negative log the concentration of the hydronium ion. Okay, so if it's 2 equals negative log the concentration, then the concentration is going to equal what? Okay, so what would be the percent ionization? How do I calculate that now? Because when we solve for, well, because here it's negative log, right? So we bring the negative on the other side, so then you get negative 2 equals log of the concentration, right? That's right. And so if we take base 10 of this side, base 10 of that side, then that gets rid of the log part, and then we get 10 to the minus 2 is equal to the concentration. Okay. Whew. 10 to the negative 2 divided by 0.5 times 100. Okay. Piece of cake. Once you figured out what pH was, right? Don't forget. Okay, let's keep going. Okay, so we can also use the percent ionization of a weak base. Works exactly the same way. So in this case, you have it's OH over the concentration of our base, the initial concentration of our base, times 100. Okay. So I'll erase this. Okay. So when we're trying to calculate the pH of a weak acid or weak base solution, so in this case, these type of problems are typically going to be given your Ka and your Kb or your Kb, and then you're going to give some information about the concentration, the initial concentration of your acid and your base, and then you're going to just calculate our concentration at equilibrium of our base or our acid, and then we're going to calculate our pH. So let's see. I'm going to give you some problems here in a minute. So okay. So we know that there are going to be acids that are going to be stronger than others, and that concept of acid strength based upon that H and that A, right? Well, that's going to start changing, right? So for instance, when we talk about H and A is typically a non-metal. H is typically a hydrogen, right? So if we think about it, right, that breaking down of the hydrogen bond and that non-metal bond, the easier to do it, the stronger the acids are going to be, right? So then if we think about it, acid strength increases as bond strength decreases. So the weaker your bond strength is, the stronger your acid. The stronger your bond strength is, the weaker your acid. The intermolecular bond, yeah. And the intra, as in within that atom itself. Yeah. That's right. So in most cases, the A represents nonmetals, in most cases. And so as we go down in groups, the acid strength increases. So from top to bottom. And why is that? So for instance, hydrogen chloride is a stronger acid than hydrogen bromide. Why is that? And so it'll be easier to pull it away. So the bigger it is, the easier it's going to be pulled away. So the bigger that atom is, it's going to be easier to pull away. And then you're going to say, but what about hydrogen fluoride? Hydrogen fluoride is a weak acid, right? So, but that's a weak acid because in that context, hydrogen is such a strong bond, right? Okay. Hydrogen fluoride, not because it's a hydrogen bond, it's because fluoride is so small that it really keeps hydrogen close to it. Remember, I told you fluoride is like that bully that's like, you want to go to the bathroom? No, you can't, right? And so as we go down the periodic table, those acids get stronger. Hydrobromic acid is stronger than hydrochloric acid, I'm sorry, okay? Because hydrobromic acid is easier to pull off than. So does that make sense? Mhm. That's right. Okay, so orbitals that have similar sizes form strong bonds. So good orbitals, good orbital overlap. Orbitals that have different size orbitals have weak bonds. So that's poor overlap. So for instance, the s orbital overlapping with the p orbital, right? So those are two different orbitals. So those guys are going to have, if they're overlapping, they're going to have a weaker interaction than if they're both s orbitals. Okay. You guys, we didn't talk a lot about that. Actually, I don't think we talked about the shape of them at all. We missed it. We skipped that part. We'll go back to it. Don't worry about it. Hydrogen, of course, is the smallest element. And atoms that are larger down the group are going to be bigger, exactly, and they're going to be easier to pull out that hydrogen. So, and then the HA bond weakens as A changes down the group, and the acid strength increases. Okay. Okay, so if we go across the periodic table, right, from left to right, so from left to right, it's going to increase. So the more polar it is, the more you're going to get the H plus ion produced, right? So for instance, if we take a look at, let's see. Okay, so if we go across here, if we have H, 3P, AQ versus H, 2, S, AQ. Okay, so these are two acids. Which one is going to be stronger? Phosphoric acid or sulfuric acid? Why? No, it's actually getting smaller. Yeah, because phosphorus is bigger than sulfur. Yeah, yeah. Because sulfur is more electronegative. The more electronegative it is, that means the more it's going to be pulling that electron. So it's going to be easier for it to make that ion, so easier for it to make the hydrogen ion. So that becomes H plus easier than this guy does. Okay. That's right. That would be a stronger acid. Yeah, so as we go from left to right, the acid strength increases. Oh. I'm showing you guys on my other screen. Okay. And so this is just kind of showing us the difference between the acids. So these are pH strips. You guys are very familiar with how to use pH strips. So here they put the pH strips in two different acids. You can see the difference clearly between them. One is obviously more acidic than the other one, which is closer to neutral. So here we have these two different acids. This is another set of pH strips. These are a little more accurate because you can get the clear distinction between the colors, and that helps us get to distinguish whether or not, okay, yeah, it is definitely 10, And so in this case, to get those, they use different dyes, and each of these dyes are sensitive to pH. And so they'll have a range of pH that they'll be able to recognize. Okay, you guys already know about vinegar. Vinegar is acetic acid. Vinegar is a carbon-based acid, so all carbon-based acids are weak acids, or majority of them are. So we know that vinegar is a weak acid. Also, we drink it and put it on our, on our food, and so. So nitrous acid is also a weak acid. Anything that typically ends with OUS is typically a weak acid, relatively speaking. So here's an example of how we would set up that problem if it came up. If we had an initial concentration of 0.516 polar, minus, then this guy is going to be negative. These are going to be positive. And then we're going to end up with, at the end of the day, 0.047 of our numbers at equilibrium. And these guys are going to be roughly the same number that they started off, or what's been added. Okay. Let's skip these. Okay, so when we look at base strengths, okay, so as we go from right to left, acid strength increase. As we go from left to right, base strength is going to increase. So if hydrochloric acid is a strong acid, then the chloride ion is a weak base. If this will be siliconic acid is a weak acid, then this guy is going to be neither acid or base. So both of these guys kind of fall into that category because they don't work as a weak acid or a weak base. Okay. Questions, concerns? Cash. Okay. So compounds that are containing the compounds that are containing oxygen and one or more hydroxide groups. So these compounds can either be acids, they could be base, or they could be amphiprotic. Okay, so this guy is going to represent the base component. This guy can represent the acid component. Okay. So if the electronegativity is low, then the bond A is going to be polar or ionic. Okay. If the And so that means that the hydroxide ion is going to be released easily. If the metal has a low electronegativity, and so it's going to be considered basic. And then if the metal hydroxide tends to be more basic. So for instance, sodium hydroxide. So Na, right? We know that Na has a very low electronegativity, right? Did I give you guys the electronegativity sheet last semester? Yeah, that one. Yeah, so we know that sodium is a very low electronegativity, so that's going to be a strong acid. I mean, a strong base, right? If the electronegativity is high, then bond A is going to be covalent. And then so we're going to get pulling at bond B. So then that's going to give us our acids. Okay, so then an example of that is, so we have let's go. Obviously, if it was F there, that would be clearly, it's going to be pulling here, right? If we have, let's say, silver Ag or 10 SN. So if you guys look at 10 I believe is so gold hydroxide. Acid or base? It's going to be an acid. It's not as an acid. Okay. Okay, so here, this is nitrous acid. Right? We also know that this is already a weak base. Nitric acid, that guy's going to be a strong acid. I'm sorry. Nitric acid is going to be a weak acid. Nitrous acid is going to be a weak acid. Nitric acid is going to be a strong acid. Let me clear this so I can see. And so you guys can see. I know it's hard to see because of that. Okay. Okay, so sulfuric acid, weak acid. Sulfuric acid, strong acid. Okay, and that's because you have these oxygens that are going to be acting more to cause this guy to be even less electronegative. Okay, questions, concerns, Cash, Kool-Aid. Okay. So, metalloids and elements that are near metalloids have intermediate electronegativity. So they have the ability to be acids and bases depending on who they're pairing up with, right? So this guy, in this situation, what's going to happen? What was that? What's going to happen in this situation? What are going to be the product? Who's acting as the acid? Who's acting as the base? There's no H2O here. So this is basically a base. So if we put it in a base, so what's going to happen to it? What's going to happen to this guy? It's going to be the conjugate base. I did this earlier, this last week. Yep, this is all one unit. Right? Okay, you're saying H2O3. You would actually take it up from here. Yeah. So then you'd have H2O2. OH. Now 4 AQ. Sorry, I screwed that up majorly. H2O2. And this is OH4. Okay, and then we'll get plus water. Because we're going to be pulling one of the hydrogens here, making it one more OH. What about here in an acid? What's going to happen? Yep. So that's right, H2O4, AlH2O4. OH2. That's right, H2O. Okay. Piece of cake. What are we doing next? Okay, one more thing and then we'll stop. Okay. So the last thing I want to talk about is the hydrolyzation of salts. Okay, so this is kind of figuring out whether a salt solution is going to be acidic, basic, or neutral. Okay. And then we're going to show you how to calculate the various species of salt, concentration of salts, and then how to describe whether or not the acid ionization, describe the acid ionization of hydrated metal ions. Sorry, I've been talking all day. Okay. So we know that a neutral solution basically has equal concentrations of hydronium ion and the hydroxide ion. So a reaction between an acid and a base is called an acid-base neutralization reaction. And then in this case, we have an acid and base. The products are always going to be exactly the same if they are completely neutralized. You guys remember what those products are. For an acid-base neutralization. What was that? I said that the hydroxide ion and the hydronium ion are going to be equal when it's neutral, when the solution is neutral. So what are going to be the products of an acid and base reaction? So generically, if you have HA, reacting with, say, M for metal, OH. What are we going to make? Say it again. I can't hear you. We're going to get what? HB. Okay. Do you guys remember this? Back in the day, switching partners. H2O, yes, that's right. We're going to get H2O and a salt. So Ma is going to be a salt. So an example, if we have sodium, I'm sorry, we have hydrochloric acid and sodium hydroxide. Don't forget everything that you learned. Like, yeah, we talked about that last semester. We don't do that anymore. So we know that gets water. NaCl. Okay, let's stop here and then we'll pick it back up. As I say on Wednesday. Today is Wednesday. Oh God, I have a meeting tomorrow. I don't want to go to. Oh my gosh. Questions? No questions? You have a question? Oh yeah. So cover slips and microslides and droppers. So if you guys, yes. So if you guys can see if we have any cover slips in that drawer and there's slides in the micro room. Yeah. And we need cover slips. Actually, we need we need like 2 packs at least. What was that? Cover glass, yeah. Yes, perfect. It's droppers. So get pipettes. Yeah, get some of those because we have a box of those. And then there's also these little glass droppers as well too. Get both of those. Glass droppers. They're in the no, actually they're next to the sink in the prep room. And then on the side they'll be like they screw on top of bottles. Can't miss them. So, and then also the plastic ones as well too. I don't know which one she's making. Okay, I will see you guys